In this section, we're going to look at magnetism. Let's start by defining magnetic force. Magnetic force is force that exists between current carrying objects. Okay, this is force between current carrying objects. Okay, now if you remember, electrical force was force between charges, but this is force between moving charges. Okay, you can say or force between charges moving with respect to each other. That's what current is with respect to each other. Okay, so if you have two wires carrying current, these two wires will exert force in each other just because of the motion of the charges, and that kind of force is called magnetic force. Electrical force is just between charges, like stationary charges, but if the charges are moving, there will be magnetic force in addition to the electrical force. Okay, now you might ask, what is the source for the magnetic force exerted by permanent magnets? Okay, we've said that magnetic force is due to currents, right? Now, in the case of permanent magnets, the magnetic force has to do with the motion of electrons around the nucleus. If you look at the Rutherford model of the atom, you got protons and neutrons in the center, and then you've got electrons moving around like this. Okay, so the source of the magnetic force is the motion of the electrons around the nucleus, which is the same thing as a current. Okay, so in this case, the source of the force of the magnetic force is motion of electrons around the nucleus. Motion of electrons around the nucleus. But then you might ask, all elements have electrons revolving around the nucleus, but not all elements are magnetic. Okay, we have only like a few, like iron, cobalt, and nickel, that are magnetic. Okay, so what's the reason? Well, for most of the elements in the periodic table, the magnetic properties of the electrons cancel each other, but for some elements such as copper, iron, and nickel, the magnetic properties of the electrons do not cancel each other, so the atom will have a net magnetic moment. Okay, so for most elements, the magnetic properties of the electrons cancel each other. And they are not magnetic. But for elements such as nickel, cobalt, and iron, the magnetic properties of the electrons do not cancel each other, and we have a net magnetic property. But for the elements iron, cobalt, and nickel, the magnetic properties of the elements do not cancel each other. The magnetic properties of the electrons do not cancel each other. And so these elements have magnetic properties. So they have magnetic properties. They have magnetic properties. Okay, so most elements are not magnetic, even though they have electrons revolving around the nucleus, because the magnetic properties of all the electrons cancel each other. But for elements such as iron, cobalt, and nickel, the magnetic properties of the electrons do not cancel each other, and the atom is magnetic. Okay, but then you might ask, if you take a certain iron sample, even though it is magnetic, its electrons have magnetic properties, normally it's not magnetic. So why is it? Okay, so normally the magnetic properties of the atoms are distributed randomly. Okay, so since they are distributed randomly, they will cancel each other. Okay, the magnetic properties of the elements are distributed randomly and they cancel each other. But if you place this in the presence of another magnet, let's say, this magnetic properties of the atoms will be aligned in the same direction, and the atom and the iron sample will develop magnetic properties. Okay, so a magnetic sample such as iron is normally not magnetic, even though its atoms have magnetic properties. Its atoms have magnetic properties, or called magnetic moment. Okay, what's the reason? This is because the magnetic properties of the atoms are distributed randomly and they cancel each other. This is because the magnetic properties of the magnetic properties are distributed randomly and they cancel each other. Are distributed randomly and they cancel each other. They cancel each other. But in the presence, let's say, of a permanent magnet, this magnetic properties will be aligned in the same direction and the sample becomes magnetic. Okay, but in the presence, let's say, of a permanent magnet, the magnetic properties, or let's say magnetic moments, will be aligned in the same direction. Will be aligned in the same direction. And the sample becomes magnetic, and the sample becomes magnetic. Okay, so when the sample is in the presence of another magnet, you see the magnetic properties of the atoms will be aligned in the same direction, and so this sample will become magnetic and will develop magnetic properties. All right, now let's look at magnetic field. You remember in the case of electricity, we talked about electric field. Electric field is a physical quantity used to represent electric force. You see, instead of saying two charges exert force each other like this, where there is nothing in between them, we say this charge sets up field throughout space, and that field exerts force on the other charge. We have the same thing in magnetism. Let's say we have two permanent magnets. If there is nothing between them, they will exert force on each other. Okay, so we say this magnet sets up magnetic field throughout space, and that field will exert force on this other magnet over here. Okay, so it's a similar concept. So you can say this is used to represent magnetic force. It's another way of talking about the magnetic force. Use it to represent magnetic force. Okay. Now the unit of magnetic field, units of, we're going to use B by the way for magnetic field. Unit of B magnetic field is called Tesla. Tesla abbreviated by capital T. Okay. So how is magnitude defined? Now, if you place a current carrying loop in a magnetic field, there will be torque acting on the loop. The magnitude is defined to be as the torque on the loop per unit area, per unit current, when the field is parallel to the loop. Okay, so the magnitude is defined to be the torque on a current carrying loop, per a unit area of the loop and a unit current when the field is parallel to the plane of the loop, okay. Will be clear later when we talk about torque, but for now, if you place, let's say you have a current carrying loop like this. If you place it in a magnetic field like this, let's say you've got a magnetic field in this direction, okay, the torque of this object per unit current, per unit area is what you call the magnetic field. So it is the torque per unit area, per unit current, when the field is parallel to the surface. Okay. All right. And the unit is called Tesla, the SI unit. As you can see from here, it is unit of torque divided by unit of current, unit of area. Okay. Torque is Newton meter, and area is amp. This is meter squared. So you can say the unit is a Newton per ampere per meter, and that's defined to be the Tesla. Okay, that's the unit of magnetic field. So magnetic field is a physical quantity used to represent magnetic force, and its magnitude is defined as follows. Okay, and then let's talk about magnetic field lines. Magnetic field lines. These are lines used to represent magnetic field. If you remember, in the case of electric field, also we talked about electric field lines. They're lines used to represent electric field. Okay, we'll do the same thing for magnetic field. We're saying that if you've got a permanent magnet over here, you see, instead of saying it exerts force on a certain another magnet over here, we say this sets up magnetic field throughout space. So this field is a property of space. So magnetic field lines are lines used to represent that field geometrically. Okay, so it's the same concept as electric field lines. All right, so if these lines are to represent the field is a vector, they should represent both the magnitude and the direction. Okay, so the magnitude is represented by the density of the lines, or the number of lines per unit area. Okay, the magnitude of the field, is represented is represented by the density, or you can say the number of lines per unit perpendicular area, per unit perpendicular area, okay, of the lines, by the density of the lines. The greater the density, the greater the magnitude, okay. For example, let's say I have this field, it becomes less dense and less dense goes away, so you can say that the field in this area is higher than the field over here, because these lines are denser over here, okay. How about the direction? Okay, so the line of action of the field is represented by the line tangent to the curve. The line of action of the field, the line of action of the field is represented by the line tangent to the curve at the given point, okay. So let's say you have this field over here like this. If you take this point, this tells you the line of action of the field over here is tangent to the curve at this point over here, okay. But there are two possible directions. It could be this way, it could be this way. How do you distinguish between these two possible directions? To distinguish between these two possible directions, a direction is placed on the lines, okay. If the arrow is this way, it means you take this direction over here. If the arrow is this way, it means you pick up this direction over here, okay. So to distinguish between the two possible directions, of the tangent line, of the tangent line, an arrow is placed on the curves. An arrow is placed on the lines, okay. So if I have this curve over here and we place an arrow over here and we're trying to find the direction of the field over here, you take the tangent line and then of course the arrow tells you we have to pick this direction. But let's say we have another one like this and you're trying to find the direction over here, you draw the tangent line, but the direction will be this way, okay. So the line of action is represented by the line tangent to the curve as a given point, and an arrow placed on the curve distinguishes between the two possible directions of the tangent line. All right. And now let's talk about magnetic poles. Now, if you have a permanent magnet of a certain shape, let's say such as a rectangular shape over here, there are two locations where the magnetic field is the strongest. For example, for this one, the magnetic field will look something like this. Okay, they will come out like, they'll go like this. Okay, so you see these magnetic field lines, they're less dense over here, but as they go to the pole, they get closer and closer. So that means the magnetic field is increasing as they get closer to this end. The same thing over here. The magnetic field gets stronger and stronger as you go to this end over here. So these two locations where the magnetic field is the strongest are called the poles of the magnet. Okay, so you can say that for permanent magnets of certain shape, okay, there are two locations where the magnetic field is the strongest. The magnetic field is the strongest. Okay, these locations are called the poles of the magnet. Okay, so in this case, this one is a pole, this one is a pole. These locations are called poles. Poles. Okay, so how do you distinguish between these two poles? Well, experiment will show that, you know, two ends will, if you have two permanent magnets, two ends might attract, two ends might repel. Okay, so that tells you there are two kinds of poles. Okay, so we should distinguish between those two poles. Okay, so how do you distinguish between these two? Well, if you let a magnet rotate freely about a pivot, the magnet will align itself in the north-south direction of Earth. Okay, if you let a magnet rotate freely, okay, it's going to align itself something like this in the direction of the north-south poles of Earth. Okay, now this end, this pole that points towards the North Pole is called the North Pole. We call this one the North Pole. Okay, and the end that points towards the South Pole, this one over here, is called South Pole. Okay, so that's how we distinguish between these two poles. When you let a permanent magnet rotate freely, it's going to align itself along the north and south pole of Earth. It will be a little inclined from the actual geographic, but it will be approximately in the north-south pole. So the end that points towards the north is called the north pole of the magnet, and the end that points towards the south is called the south pole. Okay, so when a permanent magnet is pivoted to rotate freely, pivoted to rotate freely, it will align itself in the north-south direction of Earth. It will align in the north-south direction of Earth. Okay, of Earth. Now the pole that points towards the North Pole is called the North Pole. The pole that points towards the North Pole, towards the north, let's say, is called the North Pole of the magnet. It's called the North Pole of the magnet. North Pole of the magnet. And the end and the pole that points south, and the pole that points south is called the south pole of the magnet. It's called the south pole of the magnet. Okay, so that's how we distinguish between the two poles. Okay, you let a magnet rotate freely. That's how compass works. Okay, so it will rotate and will align itself in the north-south direction of Earth. Okay, one of the poles will point north and the other end will point south. Okay, so the pole that points towards the North Pole of Earth is called the North Pole, and the pole that points towards the South Pole of Earth is called the South Pole. Now, experiment shows that similar poles attract and opposite poles repel. Okay, if you bring the North Pole of one magnet to the North Pole of another magnet, they will repel. If you bring the North Pole of one magnet to the South Pole of another magnet, they will attract. So experiment shows that similar poles repel, and opposite poles attract. Opposite poles attract. That is, north repels north, south repels south, but north pole and south pole of two magnets attract each other. Okay. Now let's see the magnetic field lines of, let's say, rectangular permanent magnet. It will be something like this. Okay, you will have lines coming over here. Now, one property of magnetic field lines is magnetic field lines form complete loops. If you remember electric field lines, they start from positive and they sink at a negative. That's how electric field lines go. They start from positive and they end in negative, but we don't have magnetic charges. So magnetic field lines actually, they form complete loops. So it might be something like this. They form complete loops, okay? So the magnetic field lines, they come out of the north pole and they go into the south pole, okay? So that's what the magnetic field line of a permanent magnet will look like. We'll have something like this, okay? They form complete loops, and the fields, they come out from north pole and they go into the south pole, okay? So this is the north pole, this is the south pole, okay? So we have the following two properties. Magnetic field lines form complete loops. Magnetic field lines form complete loops, unlike electric field lines, which originate in a positive and sink in a negative. But magnetic field lines form complete loops because we don't have magnetic charges. And the magnetic field lines, you see, they come out of the north pole and they sink into the north pole. The field lines come out of the north pole, and sink into the south and come into the south pole, and come into the south pole. Okay. So this is one of the basic difference between magnetic field lines and electric field lines. Electric field lines, they originate in a positive charge and they end in a negative charge, but magnetic field lines form complete loops. Okay, so much about the qualitative aspect of magnetism. Now we're going to get some qualitative aspect of it. Okay, now we're going to look magnetic force on a charge moving in a magnetic field. Remember, the magnetic field is produced by a certain magnet somewhere. Okay, suppose, let's say we have the following field lines like this. Let's say they're horizontal like this. All right, and then let's say we have a charge going this way. Let's say in this direction. Let's say the charge is Q. Let's say its speed is V. All right, and let's say the angle between the velocity and the field is, let's say, theta over here. Okay, so first we're going to look at the magnitude of the force on this charge. Okay, remember, this field is produced by a certain moving charges somewhere, and you've got a moving charge over here. And remember, magnetic force is force between moving charges. So there's going to be magnetic force on this one. So we want to know on what factors it depends. Magnitude, first of all, it is proportional to the field. It is proportional to the field. Proportional to the field. We're going to use B for the field. Okay, it's proportional to the speed. Proportional to the speed, that is to the magnitude of this velocity. It's also proportional to the charge. The greater the charge, the greater the force. Proportional to the charge. Proportional to the charge. Now it's also proportional to the sine of the angle between the field and the velocity. Okay, it is proportional to the angle between the velocity and the field vectors. The velocity and the field vectors. Okay, these are the factors upon which the force depends. So if you use FB for the magnetic force, we're saying it's proportional to the charge. We're talking about magnitude, so I'm going to put this on absolute value. Okay, it's proportional to the charge, it's proportional to the field, it's proportional to the magnetic velocity or the speed. It's also proportional to the sine of the angle between the velocity and the field. Now, if you notice, this v sine theta over here is a vertical component of the velocity. So you can say it's proportional to the vertical component of the velocity. That is, to the component of the velocity that is perpendicular to the field. It doesn't depend on the horizontal component. So you see, it depends on this quantity over here. This quantity over here is v sine theta. Okay, so another way of putting it is it depends on the charge, the field, and the vertical component of the velocity. Okay, let's say if the charge is moving parallel to the field, there's not going to be force because it doesn't have a component perpendicular to the field. Now, the constant proportionality is defined to be 1. So, the magnitude of magnetic force is given by the following. We have absolute value of the charge, we get the speed, we get the field, and you get the sine of the angle between the velocity and the velocity vectors. Okay, so that's how we calculate the magnitude of the magnetic force acting on a charge moving in a magnetic field. Okay, now let's look at the direction of the force. Now the direction is always perpendicular to the plane determined by the velocity and the field vector. So in this case, that plane is the plane of the paper, right? So the magnetic force is going to be perpendicular to this plane. But there are two possible directions. It could be perpendicularly in or perpendicularly out, right? It could be like this, perpendicularly out, or it could be perpendicularly in. So the first thing is the direction of the force. The direction is always perpendicular to the plane determined by the velocity and the field vector. By the velocity and the field vector. Okay, remember, two vectors determine a plane uniquely, and the force is perpendicular to that plane. Okay, but there are two possible directions, perpendicularly in and perpendicularly out, right? But there are two possibilities, so that means there are two possibilities. It could be perpendicularly in or perpendicularly out. Perpendicularly out, perpendicularly out, or perpendicularly in. Perpendicularly in. Okay, so if the field comes out like this, it's called perpendicularly out, but if it goes in this direction towards the paper, it's called perpendicularly in. Now we have symbols for these directions. Perpendicularly out is represented by a dot. Perpendicularly out is represented by a dot. Okay, and perpendicularly in is represented by a cross. You see, if you have an arrow it's perpendicular in, you see a cross, but let's say you've got a vector coming from the other direction, you just see the tip. That's why they use this dot and a cross for the directions. So the question is, how do you distinguish between these two possible directions? We know the direction is perpendicular to the plane, but we still have to determine whether it is perpendicularly in or perpendicularly out. To distinguish between these two possible directions, we have two rules that we can use. They're called the screw rule and the right hand rule. Okay? To distinguish between these two possible directions, to distinguish between these two possible directions, okay, the right hand rule or the screw rule can be used. The screw rule or the right hand rule can be used. Okay, so we're going to look at these two rules next. Okay, the screw rule and the right hand rule. So let's start with the screw rule. The screw rule. Okay, so in this case, first you have to connect the two vectors tail to tail. Okay, let's say it's the velocity vector. Let's say this is the field vector. Okay, so first connect the v as the velocity and the b vectors tail to tail. Okay, tail to tail as shown over here, and then you're going to put a screw perpendicularly to the plane. Okay, perpendicular to the plane is a screw. All right, then let's say place a screw at the intersection point perpendicularly. Place a screw at the intersection point perpendicularly. At the intersection point of the two tails perpendicularly. Okay, perpendicularly. Then rotate the screw from the v vector towards the b vector. Okay, rotate the screw from the v towards the b vector. Okay, rotate the screw from the v towards the b vector. Okay, then if the charge is positive, okay, the direction of the force is the same as the direction of the movement of the screw. The direction of the force is the same as the direction of movement of the screw. The direction of movement of the screw. Movement of the screw. Okay, remember, a screw goes in if you turn clockwise, goes out if you turn counterclockwise. Okay, so remember, a screw goes in if turned clockwise and goes out if turned counterclockwise. Okay, so in this case, you see the screw is being turned clockwise, so the direction is going to be perpendicularly in. Okay, so in this case, this screw will go in like this. Perpendicularly into the paper. Okay, so the direction is perpendicularly in this case. All right. How about if it was like this? Let's say you have B over here, you have B over here. Now you see, you put a screw over here, you're going to take this way. That is counterclockwise, and the spring and the screw goes out, so the direction is going to be perpendicularly out in this case. Okay. And if the charge is negative, the direction is opposite to the direction of movement of the screw. If the charge is negative, if the charge is negative, the direction of the force, is opposite to the direction of movement of the screw, is opposite to the direction of movement of the screw, okay? So if the charge is negative, the direction of the force is the same as the direction of movement of the screw, and if the charge is negative, the direction of the force is opposite to the direction of movement of the screw. Okay, so in this case, you see if the charge is negative, the screw is going down, so the direction of the force would be perpendicularly out. In this case, the screw is going out. If the charge is negative, the direction will be perpendicularly in. Okay. And then let's look at the right hand rule. The right hand rule. It's called the right hand rule because we have to use our right hand. Okay. So the first rule is align your fingers in such a way that the thumb is perpendicular to the fingers. Okay. The thumb should be perpendicular to the plane of the fingers. Okay. So first, align your thumb to be perpendicular to your other fingers. Okay. All right. And then we have the following. Thumb represents this magnetic force. Thumb represents magnetic force. Okay. And the index finger, or this middle finger, the index finger, this one over here, represents the velocity. Index finger, that is this one over here, okay, represents the velocity vector, okay, and the middle finger represents magnetic field. The middle finger, that is this one over here, represents the field vector. Okay, so if the charge is positive, okay, when the index finger and the middle finger are aligned in the direction of V and B, thumb represents the direction of the force. Thumb represents direction of force. But if the charge is negative, but if the charge is negative, the force or the direction of the force is opposite to that of the top of the thumb. Okay, so this is the rule. Okay, so if you align the index finger in the direction of the magnetic field, I mean the direction of the velocity, this one, and this one in the direction of the field, the thumb gives you the direction of the force if the charge is positive, or the thumb gives you opposite to the direction of the force if the charge is negative. All right, so let's say you have, let's say this is the velocity vector, this is the p vector. Okay, so to align this in the direction of the velocity in the field, you see it will be like this, and the thumb will point down. You see that? If you align this in the middle figure in the direction of the field and this in the direction of the velocity, then thumb points down. That is perpendicularly into the plane of the paper. Okay, how about if this is the field vector and this is the velocity vector? In this case, you can do it only if you put your fingers like this. This would be the velocities of the field, the thumb points up. Okay, so that'll be perpendicularly out in this case. Okay, this is perpendicularly in, this is perpendicularly out. This is assuming this charge is positive, and if the charge is negative, the direction should be opposite to this one. Okay, so now let's look at some examples. Okay, suppose the magnetic field is perpendicularly out. You see, the magnetic field is coming out perpendicularly like this, like this. And let's say you have a charge going in the field in this direction. Okay, so let's say the charge is maybe 2 coulomb. Okay, let's say the magnetic field strength is 10 Tesla, and let's say the velocity with which this charge is moving is 100 meters per second. Okay, so the question is, determine the magnitude and the direction of the magnetic force. The question is, determine the magnitude and direction of the magnetic force Okay, let's start with magnitude. That is the value of FB. This is the formula. Absolute value of the charge, the speed, the field, and then the sine of the angle. Okay, so we're told the charge is 2 coulomb, that's Q. Q is 2 coulomb. We're told the speed is 100 meters per second. We're told the field is 10 Tesla. Okay, so we just have to determine the angle. So what's the angle? Look, the field is going out, the velocity is parallel to the paper, so the angle in the velocity and the field vector is 90 degrees in this case. Okay, so we have theta equals 90 degrees. All right, the velocity, the velocity and the field are perpendicular to each other in this case. So the magnetic force is 2 times 100, the speed, times 10, the field, and then sine of 90. Sine of 90 is 1. So you've got 200 times 10, that is 2,000 newtons. Okay, now let's look at the direction. Okay, we can use either the right hand rule or the screw rule. Okay, let's do it using both of them. Okay, now let's use screw rule first. Okay, so the magnetic field is going up like this out of the paper, and the field is going this way. Okay, so that's what we have the field going out and the velocity going this way. Okay, so we have put a screw perpendicularly at the intersection of the velocity and the field like this. Okay, so if I rotate the screw from this direction of the velocity to the direction of the field, what happens to the screw? You see, I'm turning counterclockwise. It comes out, that's towards south. Okay, so the direction in this case would be south. Okay, you see that? You got the velocity going this way, you got the field perpendicularly out of the paper, and then you put a screw at the intersection point. If you rotate it from the velocity towards the field, that's counterclockwise, it comes out, which is south. So the direction is south using the screw rule. Okay, south. These are our directions. You see, we have north, south, east, west, and now we have two other directions, perpendicularly out and perpendicularly in. Okay, now let's try to use the right hand rule. Remember, this is velocity, so the velocity is going this way. You see that the velocity going this way, the field is going out like this, and the thumb points down towards south. Okay, so in either case the direction is south. Okay, all right, next we're going to look at magnetic force on a straight current carrying wire placed in a magnetic field. Okay, maybe let me go to the other page. Okay, so that's what we have. Let's say we have this magnetic field. Okay, and let's say we have a wire of length L, let's say, and let's say it's carrying current, let's say in this direction. Okay, so let's say the magnetic field is represented by B, let's say the current is represented by I, and let's say the length of the rod is L. Okay, and then let's the angle between the wire and the field be theta. All right, so we have the following proportionalities. The magnetic force is proportional to the current. Okay, so the current is proportional to B, which is the field. It's also proportional to the length. This is the length of wire. Also is proportional to the angle between the wire whose direction is taken to be the direction of the current, whose direction is taken to be the direction of the current. Okay, is taken to be direction of current, direction of current, okay, between the wire and the field, which is theta. Okay, so we have the magnetic force is proportional to the current, to the length, to the field, and then the sine of the angle. The constant proportionality is defined to be 1. Okay, so this is a formula for calculating the magnetic force on a current carrying wire. Remember, this field is due to a certain object carrying current. Okay, so this is force between current carrying objects. Okay, all right, now we're going to look at direction. In this case also, the direction is always perpendicular to the plane determined by the direction of the current and the field. Okay, the direction of the force is always perpendicular to the plane determined by the length and the field vectors. Okay, you've seen the direction, the length, the direction of the current. All right, so in this case we have this, the plane determined by this one and this one. Okay, and that is a plane of the paper. So in this case, the magnetic force is either perpendicularly in or perpendicularly out. Okay, and to distinguish between perpendicularly in and perpendicularly out, either the screw rule or the right hand rule can be used. Okay, so to distinguish between perpendicularly in and perpendicularly out, either the screw rule or the right hand rule can be used. The screw rule or the right hand rule can be used. Okay, so we have already discussed these rules. So if you're using the screw rule, rotate from the direction of the current towards the field. So in this case, you have to rotate from the direction of the current towards the field. Direction of the current towards the field. Okay, and if you're using the right hand rule, the direction of current is represented by the index finger. Direction of current is represented by the index finger. Okay, direction of the field, direction of field is represented by the middle finger. Direction of field is represented by the middle finger. Okay, then thumb represents the direction of the force, represents the direction of the force. Okay, all right, So this gives you the magnitude. It depends on the current, the length, the field, and the sine of the angle. And you can use either the screw rule or the right hand rule to determine the direction of the force. Okay, let's look at an example. Suppose the field is perpendicular into, like this. Okay, let's say the field strength is let's say 5 Tesla, and let's say we have the following wire. Let's say the current is going this way, and let's say the length is maybe 2 meters. Okay, and let's say this is carrying a current of maybe 2 amps. Okay, so I've got a current of 2 amps over here, the length of the rod is 2, and the magnetic field is 5 Tesla. Okay, the question is determine the magnetic direction of the magnetic force. So the question is determine the magnitude and direction of the magnetic force. Okay, let's start with magnitude. We saw that the formula is current, length, B, and then the sine of the angle. Okay, so we're given current to be 2 amps, the length to be 2 meters, and the field to be 5 Tesla. So we just have to determine the angle. Okay, so what's the angle? The current going this way and the field perpendicular into, like this, right? So they're perpendicular to each other. So theta is 90 degrees. All right, so you've got the magnitude of the force is the current, which is 2 amps, the length, which is 2 meters, the field, which is 5 Tesla, and then sine of 90. Okay, sine of 90 is 1, so you get 4 times 5, 20 Tesla. All right, now let's look at the direction. Okay, we're going to use both the screw rule and the right hand rule. Okay, let's start with the screw rule. Okay, so look, from the screw rule, we're going to rotate from the velocity vector towards the field. So what we have is, we have the field going down, we got the velocity going north, the field going down. Okay, and then I'm going to put my screw over here with the intersection point over here. All right, and then I rotate from the direction of the current toward the field, that is clockwise, it goes in. Okay, that is west. Okay, so the direction of the field is west. Now let's try it with the right hand rule. Okay, so remember, the direction of the current is represented by the index finger, and this direction of the field, you see, perpendicular in. You see that? I've got this, and then the thumb point is west. So you've got velocity, you got field down, and then thumb points west. So in any case, the direction is west. All right. Okay, next we're going to look at magnetic torque. On a current carrying loop. Placed in a magnetic field. Now, if you remember, torque is a measure of the rotational effect of force. Okay, so we're going to talk about the rotational effect of the magnetic field on a loop. Okay, suppose let's say we have the following loop. Let's say we have this rectangular loop over here. Okay, let's say it's carrying current in this direction, and let's say maybe we have a magnetic field in this direction, B. All right. Now, first let's talk about the magnitude. Let's say this current over here is I over here, all right, and let's say the area of this loop is represented by A. Okay, so A represents this area of loop. So we have the following proportionalities: the magnitude of the torque, is proportional to the current, is proportional to the area. The greater the area, the greater the torque. Is proportional to the magnetic field, and is proportional to the sine of the angle between the area and the loop. So we got to talk about direction of area. Okay, theta is angle between area and field. You might think area is scalar, but area is actually a vector. So let's talk about area before you go any further. Okay, area is a vector. Because you see, because area can face into different ways. This area and this area are not the same, because this area is facing this way, this area is facing up, and so on. Okay, so area has directional properties, and the direction of area is defined to be perpendicular to the plane of the area. Okay, area is a vector. Okay, obviously its magnitude is the area of the loop. Let's talk about the direction. So direction of area is defined to be perpendicular to the surface of the loop. Okay, is defined to be perpendicular to the plane of the loop. Okay, plane of the loop. Okay, so if this is the loop, okay, so the direction of the area is perpendicular to the loop. Okay, not only that, is defined to be perpendicularly out. Okay, it's also defined to be perpendicularly out. It's also defined to be perpendicularly out. Okay, so the direction of the area over here is defined to be, there are some possibilities, perpendicularly in or perpendicularly out, but the direction of area is defined to be perpendicularly out. So this direction is the usual direction pointing towards here. Okay, perpendicularly out is the direction pointing towards here. The direction pointing towards here. Pointing towards here. If you're not sure, you can use the right hand rule. Okay. Put your fingers around the loop in a counterclockwise direction, then the direction of thumb will give you the direction of area. You can also use the right hand rule to determine the direction. Okay. You can also use the right hand rule, the right hand rule to determine the direction of the area. The direction of the area. So if fingers are placed on the loop in a counterclockwise direction, like this, thumb gives you the direction of the area. Okay? So when fingers are wrapped in a counterclockwise direction around the loop, okay, thumb gives you direction of area. Thumb gives you direction of area. Okay, so like this, you see it. In this case, this is a counterclockwise direction, you see it. So direction will be perpendicularly out. You put your fingers around the loop in a counterclockwise direction, and the thumb will give you the direction of the area, which is perpendicularly out. Okay, so when you talk about the angle between the field and the area, that's what we're talking about. The area is perpendicular to the plane of the loop, and then the angle is the direction between that direction of the area and the field. Okay, so with that, the magnitude is defined to be the torque. It's not magnetic. This is the magnitude of the torque. So we're going to use tau for the torque. Okay, magnetic field. That is current, the area, the magnetic field, and then we got the sine of the angle between the torque, between the area and the field. But in this formula, you gotta be careful about the current. Okay, current is taken to be positive if counterclockwise, and well, this is magnitude, so let me just put upside value. This is magnitude. So we have magnitude of the torque is the upside value of the current times area times b times the sine of theta. All right. Now let's look at the direction. Okay. So the direction is perpendicular to the plane determined by the area and the field vector. Okay. The direction is always perpendicular. The direction is always perpendicular to the plane determined by the area and field vector. Okay, and of course there are two possible directions, perpendicularly in and perpendicularly out. Just like before, we can use the right hand rule or the screw rule to distinguish between the two. Okay, to distinguish between perpendicularly in and perpendicularly out. Okay, the screw rule or the right hand rule can be used. The screw or the right hand rule can be used. Okay, if you decide to use the screw rule, you have to rotate from the area vector towards the field vector. Okay, rotate from the area towards the field vector. The field vector. If you're using the right hand rule, okay, you got to align the area vector along the index finger, and the field vector along the middle finger, the field vector along the middle finger. Okay. All right. So if the current is counterclockwise, the direction is the direction determined by the screw or the right hand rule. But if the direction is clockwise, the direction is opposite to the direction determined by the screw rule or the right hand rule. Okay. So if the current is counterclockwise, if the current is counterclockwise, the direction of the torque, is the direction determined by the screw or the right hand rule, determined by the screw or the right hand rule. Okay. But if it is clockwise, the direction is opposite to that. The direction is opposite to that. Okay. So it matters whether the direction of the current is clockwise or counterclockwise. Okay. All right. Now let's look at the rectangular loop we have over here. Maybe let me put it again over here. So we have this rectangular loop over here. Let's say it's carrying current in a counterclockwise direction. Let's say the field is going this way like this. This is B. This is the current. Okay. Now, let's see what the field is doing to this loop. Let's look at the force on each wire over here. You see on this wire, you see the length is going this way, the current's going this way, right? And the field is with the parallel. The angle is 0, sine of 0 is 0, so there is no force on this one. Same thing over here. The current's going this way, the field is going this way, the angle is 180, sine of 180 is 0, so there is no force over here. Now let's see what's happening over here. Now the current's going this way, right? And the field is this way. So if you use the screw rule, you put your screw at the intersection point, you rotate it from the current towards the field, it goes in. So the magnetic field is actually pushing down over here. But on the other side, you see the field is going this way, the current's going this way. You see the direction of the current is reversed, so the screw goes out, perpendicularly out. So the direction of the magnetic force over here is a dot. All right, so you see what's happening? This wire is being pushing up, this wire is being pushing down. The effect is to rotate. That's why we're talking about torque. So the effect of the magnetic field on this loop is rotation. Okay? All right. And so let's determine the direction of the area now. The direction of the area. For the area, you always put your fingers in a counterclockwise direction. So the direction of area is a dot in this case. You see, you've got this plane, and the area is perpendicularly out. So direction of area is a dot perpendicularly out of the paper. Okay, so what's the angle between the area and the field? So this is the area, the field this way, so this tells you theta is actually 90 degrees in this case. All right, so which way is rotating? Let's say this is the axis of rotation over here. Okay, so it's going to be push it down over here and push it up over here. Okay, so it's going to rotate this way. It's going to rotate this way, right? It's going to be push it over here, push it down over here, and push it up over here. Okay, that is counterclockwise. That's seen from the top. All right. Okay, so let's consider an example now. Example. But I think before that, let me talk about the relationship between the direction of torque and direction of rotation. Okay, let me look at the relationship between direction of torque and direction of rotation. That's whether it is clockwise or counterclockwise. Okay, so you see in this case, this is the direction of the torque. We have area going this way, the field, the area is going this way, the field is going this way, so when you rotate from the area towards speed, go this way. This is the direction of the torque, right? And we just conclude that it's actually rotating this way. So we're talking about the relationship between this direction and the direction of rotation. See, so when it's up, it's going to be counterclockwise. But let's say the direction of torque is this way, it's going to be clockwise, okay? Let's say the direction of the current is reversed. This will be a dot, this will be a cross, and go the other way, and the torque will be down, okay? So basically, a positive torque is related with counterclockwise, and a torque in the negative direction is related with clockwise. So direction of torque and direction of rotation are related by a right hand rule. So direction of torque and direction of no, I should say direction of rotation. Direction of rotation are related by the right hand rule. Are related by the right hand rule. Okay, so when thumb is aligned in the direction of the torque, fingers give you the direction of rotation. Okay, so when thumb is aligned in the direction of the torque, in the direction of the torque, fingers give you the direction of rotation. The direction of rotation. Okay, so if the torque is this way, it means the direction of rotation this way. But if the torque is down, it will be reversed, counterclockwise, right? So this, if this is the direction of the torque, this gives you the direction of rotation. All right, that's how they're related. All right, let's look at an example now. Maybe let me go to the other page. Example. So let's say we have this rectangle over here. Okay, let's say this is maybe 0.4 meters. Let's say this one is 0.2 meters. And let's say it's carrying current, let's say in this direction. Okay? And let's say the magnetic field is this way. Let's say the magnetic field is 10 Tesla, okay? And let's say the current over here is maybe 5 amps, okay? So the question is, determine the direction, the magnitude and direction of torque, as well as the direction of rotation. Okay, let's start with magnitude. Okay, the formula for the torque is the current, the area, the field, and then sine of theta. Okay, so we're told the current is 5 amps, the area is 0.4 times 0.2. okay, it's a rectangle, so it'll be 0.4 times 0.2, which is 0.08 meters squared. And the field, we're told, is 5 Tesla. Now let's determine the value of the angle. Now you see the direction of the area is perpendicularly out. The field is parallel to the plane of the paper, so the angle is 90 degrees. Okay, so the torque would be the current 5, the area 0.08. Okay, and then B is 10 Tesla, and then you got sine of 90, which is 1. Okay, so this is 0.4 times 10, that's 4. So the torque is 4 Newton meter. Okay, next let's do direction. So first we have to figure out the direction of the area is perpendicularly out. The direction of field is this way. So if you use the scroll rule, you see you have the direction perpendicularly out, the field going this way. So you rotate from the direction of area towards the field, it's up towards north. Okay, but the direction of the current is clockwise, so we have to reverse it. Okay, so the direction of the torque is south. All right, so the direction of the torque is south, like this. So scroll rule gives north, but the direction is south because the direction of the current is clockwise. But the direction of torque is south because the current is clockwise. The current is clockwise. Okay, so the direction is south. Okay, now let's look at the direction of rotation. Okay, so it's south, you see, means the thumb is pointing down and then it rotates clockwise. Okay, so you see when thumb points in this direction, it's going to rotate in a clockwise direction. You see what's going to happen? You got the field going this way, you've got the current point down, so you go from the current towards the field. What happens is perpendicularly out. But if you go over here, you got the field going this way, you got the current going this way, so it's being pushed on this side, it's being push it up this side, so it rotates in a clockwise direction. All right. Okay. Next, we're gonna look at mass spectrometer. Mass spectrometer. Spectrometer. This is a device used to separate charged particles according to their masses. This is a device used to separate a mixture of charged, I should say same charges, charged particles according to their masses. According to their masses. Okay, it helps us to separate particles according to their masses. Let's say we have this field over here. Let's say this is perpendicularly out. Okay, so what happens if you propel a charge in this direction? Let's say with velocity v, let's say the charge is q. Let's assume it's okay, so the velocity is this way, the field is this way, so you got the velocity going this way, you got, maybe I should start right here because going, let me do the other page. Let me do the other page, too small. So let's say we have this field over here, this field over here. Okay, and then I propel a charge, let's say a positive charge q, with the speed v over here. What's going to happen? The velocity is this way, the field is this way, you rotate from velocity of the field is going, push it up towards north, okay? Okay, so this will be deflected, but once again, it will keep being deflected. So if you have a force that's perpendicular to the trajectory, the result is a circular trajectory, okay? If the effect of force is only to change the direction and not the magnitude, then the trajectory is going to be circular. You remember circular motion from last semester, okay? If you've got a centripetal force acting on this object, then the effect is to go in a circular path, okay? So this is going to go in a circular path. So, and then let's say it might come out over here, the particle, okay? Because the force is always perpendicular to the trajectory, it will keep deflecting towards the center, and then finally will come out over here. Let's say the radius of this circle, this trajectory is r, okay? So this is the force that's making rotate in a circular path, okay? So this force is actually the centripetal force. So the centripetal force is provided by the magnetic force. Centripetal force provided by the magnetic force. Magnetic force, okay? So we have the centripetal force is equal to the magnetic force. But the magnetic force is, remember, Q, the velocity times B, the sine of the angle. The angle is 90 degrees in this case. You see, you got velocity going this way, velocity in this plane, the magnetic this way, so it's 90 degree, sine of 90 degree. So the magnetic force is QVB in this case, okay? But if you remember, the centripetal force is mass times acceleration equals mass times centripetal acceleration, and centripetal acceleration is the square root of speed divided by the radius, okay? So this must be equal. So you've got m speed squared divided by the radius equals charge times speed times the magnetic field, okay? So one of the velocities goes away. So you've got mv equals radius times q times p. That tells you the radius of trajectory, this radius over here, is mass times speed divided by the charge and the magnetic field. What does it tell you? The radius is a function of the mass of the particle. So the greater the mass of the particle, the greater the radius. If you've got particles with different masses, you see the bigger particles are going to rotate in a bigger circle, like this. The bigger particles are going to rotate in a bigger circle. So you see they will be separated according to their masses. The smaller mass will come out over here, the next bigger particle come out of here, and so on. So this way, the particles will be separated according to the radius. So the important thing over here is the radius is a function of the mass. Radius is a function of mass, which means the particles will be separated according to their masses. So this implies particles will be separated according to their masses. Separated according to their masses.